All right, so we need to look at what should be the boundary conditions. So let's do a very quick sketch again. Okay, so over here we had simply supported at one end. We had a roller somewhere over here. That's really what's important. The loading is not that important in this case, but just to make sure. We had a distributed load over here, and we had a punctual load over here. And we knew the distance between A and B is 8 feet. And between B and the end here is 6 feet. All right, so we need different boundary conditions. So we have 4 knowns, C1, C2, C3, and C4. So unknowns, C1, C2, C3, and C4. So we need to have 4 boundary conditions or 4 continuity equations. So what is one of them that we discussed yesterday at the end of the class is that we know the deformation needs to be 0 at point A and point B, no? Okay, so first one would be deformation at point A is 0. So mathematically speaking, this would be represented by the equation y AB at x equals 0 will be equal to 0. So the other one is that we know the deformation needs to be 0 at point B. So we can say basically the same thing. Deformation at point B is 0. Okay, but this time, remember, this will be the second equation that we have. It will not be AB, it will be y BC at x equal what? In this location will be 8 equal to 0. Okay, but we have 4 unknowns, so that means that we need 4 equations. So we need 4 conditions. What could be the other 2 conditions? Is that we know that the deformation at point B must be the same, no? Okay, since we have y of AB from this side and y of BC from this side, at this location here, we need to have that y of AB equals to y of BC in value, but also in order for the deformation to be continuous, what needs to be equal? The slope, no? You cannot have a jump. If you want a curve to be smooth, you need to have the slope to be equal, no? Okay, so condition 3 will be the deformation at point B must be equal. I think I don't want to write like a paragraph. that's what, but the deformation at point B from YAB and YBC must be equal. So basically what it means is that YAB at X equal 8 needs to be equal to YBC at X equal 8. And because the deformation is continuous, that means that the slope at that point also needs to be equal. So for slopes, maybe put deformations instead of deformation, slopes at point B must be equal. Which this time, this will mean what? DYAB dx at X equal 8 must be equal to DYBC dx at X equal 8. Yes. So that's basically what we have. All right, so we're going to start applying each one of these equations. So let's first do the first one. Deformation at A must be equal to 0. So let's look at the first condition, Y of AB at X equals 0 equals 0. What was the expression we had for YAB? So we need to go back to the class notes. So YAB if I can find it. YAB, we had YAB of X is equal to 1 over EI minus X to the 4th divided by 4 plus 20.25 X cubed plus C1X plus C2. So basically, if we apply this condition, what are you going to get? This time will be 0, this time will be 0, this time will be 0. So you will get that C2 is equal to 0. All right, now we're going to apply this second condition. Deformation at point B is 0. So 2 Y of BC all right, so Y of BC at X equal 8 equal to 0, and Y of BC of X was given by 1 over EI 5/6 X cubed minus 35 X squared plus C3X plus C4. So basically now what we need to do is substitute the X by 8 and equal that to 0, okay? So, I mean, go ahead and do the calculation if you want with your calculator. Let me pause for a second, and what I'm going to do is that I'm going to open Maple or something like that to see if we can check our answer. But go ahead and check it on your side. Okay, so I'll open Maple, and the first thing you need to do is to type restart. Basically, it means it's going to clean everything. And here, what I need to do is just to write down Y, B, C. Maybe let's do everything here. Let's see. Y, A, B equal to 1 divided by EI times, what do we have? Minus X to the power 4, everything divided by 4, plus 20.25 times X cubed, plus C1 times X. 20.25 divided by 6. Maybe so then I copied wrong the first time here. I think you're right. It's 26 divided by 6. So let me change here on the camera. So it's 20.25 divided by 6 plus C1x plus C2. All right, let's go back to this one. So I forgot here the divided by 6 plus C1x plus C2. And that should be the parentheses. Okay, now let's do Y of BC is equal to 1 divided by EI times times 5 divided by 6. So this takes a little bit longer at the beginning, but on the long run, it's much faster. That's why I'm doing it. I mean, I have the results to tell the truth, but when I teach a class, I like to do everything from scratch with you guys. Okay. Minus 35 times X squared plus C3 times X plus C4. Oops, that's it. All right, so we should be able to do this condition with this one, but let me do another one. Let me do the other two at the beginning. So we have DYAB should be equal to what? To the differential of this one instead of integrating. Now maybe we can do this of YAB, should get the same thing, comma X. So it should give us, should be the same thing that we had before, and DYBC should be the same thing with these ones. Okay, so the first equation we did over here, maybe we don't need to do it. If X equal to 0, we had C2 will be equal to 0, no? Okay, now we need to apply the ones at X equal 8. So at X equal 8, the condition we just applied now, let's go on the next line, is that Y of BC needs to be equal to 0. Okay, so basically we can say EQ1 will be equal to this. I mean, really should be YBC minus 0, but since it's 0, it's 0 here. This will be equal to this. So this should be equal to 0, no? Correct? Okay. Now, what should be the next condition? Our next condition is, so let's see if that gives us the equation. Let's see if it gives a simplification here. Why didn't substitute X 8? Hold on one second. Should have substituted 8 here. Okay, so basically this will give us what? 1, so it will give you 1 over EI of negative 5,040 divided by 3 plus 8 C3 plus C4 equal to 0. I'll show you, I just wrote this over here. So here we cannot solve because we have one equation. How many unknowns do we have? 2, C3 and C4. So let's say this will be our equation. Roman 1. Okay, so we keep going, we don't panic. What should be the third boundary condition? Deformation at point B must be equal from the two deflection curves. So that means that we need to have y of AB at x equal 8 equal to y of BC at x equal 8. Okay, so I'm not going to write the two equations. I'm just going to do it on the maple. So this will mean what? So let's say this will mean that YAB equal to YBC. What can we write that equation as? YB minus YBC will be equal to 0, no? The same thing. And this, I'm going to call this one equation 2. And now this equation, you see, is in function of C1, C2, C3, C4, but C2 is 0. So maybe we should put C2 equal to 0 here, since we know that already. That way we'll simplify a little bit. Okay. All right, so we'll give us, what is the other equation? This one here. So we'll give us that equation there, which is 1 over EI will be equal to 704 plus 8C1. So now maybe we need to be careful here because it's a minus. So I guess plus 5,440 divided by 3 minus 8C3 minus C4. Okay, I just recopied that one. And again, now we have more unknowns. We have C1, C3, C4 as unknowns. So this will be our equation Roman numbers 2. But again, it's not a big issue because we can still write down equations. What is the last boundary condition we can apply? That the slope at the 2 points are equal. So we can over here now use the last equation, which is going to give us 4 dyab dx at x equal 8 must be equal to dybc dx at x equal 8. Okay, now go to maple, do this calculation, and basically it's the same thing as this equation here. So I can just do this, but instead of using y, what do I need to use? The dyab minus dybc is equal to 0, and we get that equation here. So this one is only in function of C1 and C3. So I'm just going to copy that equation. This is going to give us that 1 over EI of 136 plus C1 plus 400 minus C3. Okay, that's what I'll copy here. And this will be Latin 3. So now, the unknowns we have are what? C3, C4, and C1. So 3 unknowns, how many equations we have? 3. So we can go and solve for C1, C3, and C4, no? Okay, so we can write down next over here. So 12. So it means that the 3 unknowns, C1, C3, and C4 are obtained by solving the system of equations given by 1, 2, and 3. Okay, so how do we do that? In Maple, so this is where this is very good. We come over here, you only need to type solving. What are we solving? The system of 3 equations. So EQ1, EQ2, EQ3. And what are the variables we want to solve for? C1, C3, C4. Enter. And it's giving us everything in function of EI, but why is not solving? All right, maybe let's simplify this a little bit. Solving EQ1, EQ2, EQ3 for C3, C4, C1, C1, C3, C4. Maybe let's do something here. Maybe this will help. Okay, so here the only thing it did was to retype what I put over here. I don't think we need this. What happened is that I think the command is not solving, but solve. Yeah, so that's probably what it is. We come over here. And there we go. All right, so we have that C1 will be equal to negative 88. I think would be good enough. So we get C1 equal to negative 88. C2 we know is equal to 0. C3 is equal to 448. And C4 is equal to negative 770.6667. I think that should be good enough. Okay, so finally, the deflection curves are obtained by substituting C1, C2, C3, and C4 into the two equations we had before. So I'm just going to put them. So this one is 1 over EI of minus x over 4 divided by 4 plus 20.25 divided by 6 x cubed plus C1x plus C2 and YB C of x 1 over EI of 5 over 6 x cubed minus 35 x squared plus C3x plus C4. Okay, so now let's say you need to plot this. What is the way I will do this? Probably I will just, probably you can do it in Maple, but now for plotting I like MATLAB. So if I had to plot this, say on a homework, that probably gonna have to do. You see, I will use a bunch of software, no? That you have accessible. So let me close these things. I never use them. So let's say new script. So here, like in Maple, I always clear everything, clear the screen, and I will put whatever. C1 is equal to what? Negative 88. C2 is equal to what? 0. We go to the line probably. C3 is equal to 448 and C4 is equal to negative 1,770.66667, whatever. Then I think we can probably go here. Maybe we could have done it here. YAB, let's see if we had it on top. Maybe let's see if we can do this. All right, we can do that one here. And let's go for the other one. Let's see if we do any different. I'll take the top of the bottom. Okay, I guess it's kind of the same, it's the same. So now the only thing I need to be careful is what? Is that this needs to be plotted between two different intervals. So let's say x1 will be equal to what? Between 0, let's do increments of 0.1 up to 8. And x2 should be what? Between 8, increment of 0.1 up to 14. Okay, so this one should be with x1. This one should be with x2. Okay, he's put a bunch of zeros that I don't know why. Let me just remove those zeros. Okay, I think if I try to run it as it is now, it's going to give me an error because it's going to try to take all the values here for x1, no? So let's see if I run. Maybe it's going to ask me to save it first. So whatever, Untitled, it's fine. Change folder. You see, it gives me an error of deep power. So, okay, so let's follow the recommendation. We just need to put the point. I will have put it also in front of the multiplying values, but if that one works. just for this one. Okay. Oh, yeah, that one is very silly, the error. Let's do a simplification. I mean, EI for simplicity, let's say is equal to 1. We'll run it. Okay, no error. So now let's see, we can maybe go and plot it. So let's say plot. Let's see, x1, YAB, and x2, YBC. I like to put the grid on personally. X label, maybe we can say whatever, span in fit. And on the Y axis, so Y label will be deflection curve, which is Y of X. That one will also be in fit according to the units we have been using. Okay, so basically, it will give us something like this for these values. Okay, that makes sense because the load was down over here and it was down at the end, no? So this point here will be the point B, this is point A. Okay, so I think from another semester, I put some of these files, they might be a little bit different, but otherwise I can save these ones if you want to put them, but the other one should be kind of similar. Whatever you want me to do, okay? Just let me know at the end of the class. Since we're doing software, let's stop for a second and let's look at some more software and then we move ahead with another problem. All right, so we did this one, 11, 12, 10. Here, really what I want to show you is that how could we check these figures over here? So basically the shear and bending moment. Okay, so in order to do that, what we're going to do is that we're going to use FEMAP, which I don't think you have used before. If you have done, that would be great. But you type over here FEMAP. This is a final element program. Okay, so I guess I don't know what will happen. So this is the program. So we first need to create the geometry. So let's say create the curve line points. You can type here 0. We know it's 14 in length. So this will be Control A will center the figure. You roll it, you can zoom in and out. So now we need to do the meshing. So basically to give some physical representation. The material doesn't matter because the shear and bending moment diagrams are not affected by the material. Okay, it's like the load, no? You can apply the load on the table. You will know what is the shear bending moment diagram. Then how much it's going to deform, it depends if the table is made out of wood, steel, or another material. But it should not affect the shear and bending moment. So here, let's just put any materials. If you want, I can just put here 1 if you want. And here, let's say 0.3, where I could just load any one of these materials. Okay, really should not matter at all. Okay, I want to select any of this one. Let's say here, okay. All right, so deselect the material. Now, properties, not gonna get in detail. Select the material. Here, we're gonna select a 1D element, which is beam. Not gonna get in detail. Simplification. Let's use a simple geometry. Whatever you want, let's use a rectangular bar, and let's say this is huge, 1 by 1, but who cares, okay? It's not realistic, no? 1 foot by 1 foot. I mean, maybe if it's 14 foot long, well, whatever. I'm gonna make sure this is for the y-axis. Since the y-axis here is going up, I just wanna, for simplicity, I'm gonna make sure it's going in that direction. And you see, this will calculate all the moments of inertia and everything when you need to calculate the formation. But my goal here is just to show you how to find the shear and bending moment diagrams. So we have the property. Now we need to do the meshing. So mesh control, size along curve. This is like when you do integration by hand. If you have multiple little spaces, the accuracy of the integration is going to be more accurate, no? Okay, so here the minimum will be 14. Let's put 14 at the first time. Obviously, the result should not be perfect, no? But it should not be bad. If you want to have a better result, probably it's better to put more elements. So I put 14. The reason I put 14 is because then at 1, I will know it's 1 foot, and so on and so on. So I put this. Now I do mesh geometry curve. I'm going to mesh that with whatever property we just created. All right, and I'm going to say the Y is going up. You should see an arrow going up now in that direction here. Preview, you see. So we know basically in here what it means is that you could be oriented this marker. The cross section could be this way, or any other way, no? But specify the direction. You make sure that you put it in the direction you want. Again, in order to find the shear bending moment diagram, it's not important. And even this one is a square, so it doesn't matter at all. Okay, now we need to apply the boundary conditions. So what were the boundary conditions? So for boundary conditions, we had pin over here and a roller over here. Okay. So here you need to be a little bit careful because this is really, even though this is a 1D element, you can put a title here. So let's say constraints, but you don't have to put anything. So at this point, really simply supported. So if it's simply supported, what does that mean? That it cannot move on the X and Y, no? Yeah, this cannot move on the X and Y. But this is 3D. So let's say it can also not move on the X. And now this is free to rotate about which axis? This is free to rotate about the Z axis, no? So you need to leave the Z axis free and constrain these two. If you don't do it, it's going to give an error. If you want, we can run it and you will see we'll give you an error. But basically, this is free to rotate about the Z. Okay? We put it here. Now, the other one was located at 8. We want to show you, I mean, you don't need to do this, but tools, work plane, draw work plane. So this will tell you the next one should be at 8. So right here, it's done. So model, constraint, nodal at 8 will be this one. Now this one is the roller. So this one should be able to move on the X, no? But also to rotate about the Z. So in this case, it's able to move about the X, so you don't check it. Cannot move on the Y, cannot move on the Z, cannot rotate on the X, cannot rotate on the Y, but should be able to rotate about the Z. Okay? And you click OK. All right, now next we need to apply the loading. All right. So let's do here model load. Let's start by the one at the end. One here, this is loads. The one at the end over here was equal to what? -5. So we put here force on the y direction. -5. Okay, it should show up over here. And now we have a distributed load between point A and point B. So this one, you need to do model load. Instead of being nodal, this is going to go along the elements. So I guess you do elemental. You need to choose all these elements. You can choose one by one, or you can go here to pick box and do this. And basically you see those 1, 2, 3, 4, 5, 6, 7 elements, 8 elements are selected. You click OK. We have a distributed load. What is the value of the beginning of the distributed load? -6, and at the end, -6. So we have -6, and -6. And we can click OK. Element of Y is the same as the global, but if you want to put either one in this case, OK, and it should show over here that way. All right, so let me save this. Where can I save this? Desktop, new folder, temp. Model 1. Save. Okay, now you need to run this. You can almost everything you can do it using this menu here, or you can do it from here. Okay, so if you want, I'll show you the next one from here. Right click, manage, new. We use the static solution. You can just say okay and analyze. I'm not going to get into too many details, and this should be pretty quick to run. I mean, the computer was okay. Now that's it. It's done. All right. Has the results been transferred? Yes. So results. And now you click on F5. We're going to use first, we're going to look at the beam diagram first, deform. And we want to look at what? So for the, let's first look at the moments. So we look at the moments, that will be 3014. I mean, here let's put total translation, doesn't matter. And here would be 3014 for the moments. Beam diagram. And this is what we get. Okay, so what did we get before? That was the figure. So we got the basically the same thing, no? On shape or form. But here, be careful, because now if you look at it, is this value exactly the same one? You see this one, the maximum value here is 33.75. But here, the value we obtain theoretically is 34.17. So why are we getting a smaller value on the final element? It's because this size of this division here is pretty large, no? If you make the, if you break this in two, probably you're gonna get a value that is closer. Okay, so I'm not gonna redo it, but you could redo the same thing, but applying different values. I mean, I can show you that can be done very quick. Delete, results, preserve, undo. Now I can do delete, model, load sets, because that's going to change. Okay, okay. And I could come here. I could do different ways, but you can click here on meshing. No, this is meshing. Meshing size. Increase by 2. You select the curve. And it has increased this by 2, no? Now you need to go very quick, do the same thing. Model, constraint, nodal. So we had this one, the first one was what? TX, TY, TZ, RX, RY. And then we had the other one at 8. That was basically the same thing, but could move on the X. Okay. Now model, load, nodal. I'm going to put a title. Here we had 95. And model, load, elemental, big box. All of these ones, okay. Distributed, 96. 6. And okay, okay, the same thing. Save, run. Okay, did it finish or not? I don't know what it did. Okay, did not run it. So let's see what's happening here. All right, look like it's finished. I don't know what happened before. So again, you see, you get exactly the same thing, but this time, you remember before we had, what was the maximum value? 33 point something, no? Now what do we get? 34.13. So we got closer to the value that we need to be 34.17. All right. So you see, this is just due to the mesh size. So now the other one we need to look at is that what would be the shear diagram. So the shear diagram, you're going to see what happens is that it's going to have the same shape, but it's going to be like reverse. And the reason is because he's not looking at the force, he's looking at the reaction. Okay. So you come here, F5, deform, and instead of being 3018, I think it's 3014, it's 3018. You click over here, click, and basically it's the same thing that we had, but reverse, no? Okay, it's because instead of looking at the force, it's looking at the reaction. So, but you see it from 20.25 to minus 27. So obviously the first one here should be identical, minus 20.25. But that one should be what, 27.75, and the value here for us was, well, it's pretty good, 27.75. So in this case, it's going to give you the exact values. Okay. So again, because we don't have the correct, I didn't do the calculations to have AI equal to 1, but let's say you wanted to check the deflection curve. What could you do? You could come over here. Let's say you could put total translation, but let's just make sure we see just the Y. This is what you will have, which is what we had, no? I think on this one, I don't see the figure. Let's rerun it very quick. But basically this will be the 0. It goes down, up, and down again, no? Okay. And that's basically what you see over here. It goes down, up, and down again. All right. So now you have no excuse if I give you a problem to not get the right answer, no? You can go and check it. Okay. All right. So let me save this in case you want it. Okay. So let us do one more example. And there's a reason why I do this one. Okay. So a second example here. This time we're going to look at a distributed load. So again, a simply supported beam. But this time, let's say we're going to have a distributed load. That's the value of 5 over here, 0 at the end. And let's say it's going down instead of up, okay? Okay, let's say this beam has a length L. Okay, so what we need to do here is to determine the shear bending moment diagrams. So draw shear and bending moment diagrams. And I don't know if we're gonna have time to do both cases. but I'm going to break this into two cases. So case one. Case two, case one, I'm going to say start from point B, which will be easier. And the other one would be start from point A. Okay, and in this case, L equal to 12. Okay, so let's do case one. So again, I'm going to start skipping a lot of details, but if we start from case one, it means starting from B. What does that mean? So what is the first thing we need to do? Free body diagram, no? Or a figure. On the figure, this will be point B. This is point A. So how many reactions are we going to have at point B? Just one. By. How many are we going to have at point A? 2, AY, and AX. You see, I start going faster. Okay, I did the first one in a lot of detail. Now, what's going to happen with this force over here? How much is that one going to be? 30, because it's 5 times 12 will be 60, but this is a triangle, will be half of it, no? Now, where would that force be located? Okay, 1/3 from point A or 2/3 from point B, no? So basically it will be somewhere over here. 30, and that's why I use 12, because if that is 12, what does that mean? This side over here, this is 8. Here, what are the units? And this is 4, no? Correct? So now, first thing, free body diagram. 2, we need to find the reactions. For once, I'm going to put here step 1, step 2. Find so free body diagram or figure reactions. How do you find the reactions? So we do summation of forces and summation of moments. Summation of forces on the x direction will give you right away that AX equal to 0. Summation of forces on the y will give you what? AY plus BY equal to 30. It will be minus 30. Okay. Equation Latin 1. And next we need to go to the moment equation. So every time you do a moment equation, what you need to do? Say about which point. So about which point you want to take it, so we can do whatever you want. A, so point A. Equal to 0. So about point A, what are you gonna have? You're gonna have BY times 12 minus 30 times 4 equal to 0. So this is going to give you what? 12 BI equal to 120. So you can see right away that BY will be equal to 10. Whatever units we're using, doesn't matter. And then what can we say from equation 1, we're gonna get that AY equal to 30 minus BY, which means that AY will be equal to 20. Okay, so for either case 1 and 2, the reaction should be the same, no? Okay, so we don't have to redo that. So part 3, shear and bending moment. Shear and bending moment. So over here, we said that we're going to start from point B. So what does that mean? How many cuts do we need to do in this problem? Obviously, we only need to do 1 cut, no? Okay, so let's say 1 cut, whatever you want. Well, let's say we cut it there, but we're going to start from point B. So we have point B here. This is our cut. This is point B. So we know we're going to have here shear B. A moment M. And maybe I should not have done this, but in red, but it's too late. And here we're going to have the distributed load that we know is 0 over here. So do you know the value over here on top? You don't know it because this is not at the other end, no? Yeah, this could be at any location over here. All right, so something probably we need to find is what? Probably what we need to find is that equation here of the equation of this curve. Okay, so in this case, let's see if I can do that in green. Our coordinate system is going to start from this end. This will be X. And this will be Y. Okay, so part little a was to find the shear. So in order to find the shear, what is the equation we need to use? Summation of forces equal to 0 on the Y direction, to be more accurate. So now let's be careful here. Well, what is that going to give you? This is going to give you what? Maybe I forgot to put something on the figure, which is what? By that we say was equal to 10. Let me just put 10 over here, okay? Or we could use by. Let me use by because that might be, at least for the first equation, I like to use by. So what should be the equation? Should be by plus V. And now, how much would be that force over here? Again, what can we do? You can replace the value of this force by what? By 1 force at 2/3, no? Yeah, okay. But maybe now you need to know what is the equation of this line. So, all right, so y of x over here is equal to what? Is of the form ax plus b, no? If it starts from the origin, so basically what would that mean? Y of 0 would be equal to what? 0, which will mean that little b is equal to 0, no? Yeah. Now, what is the definition of slope? Is the same as the tangent. What is the tangent? Is height over run. Okay. So what should be the slope from this figure? What is the height? 5. What is the run? 12. So the slope of that curve is 5 over 12 x, no? So really this y of x here is what? 5 over 12 x. Okay, so what would be the value of the force? Would be, so this would be minus, so the height would be 5 over 12x times what? The run, that should be x. Okay, and this is triangular shape. So as we did for the other one, you need to take half of that value. And this should be equal to 0. So now, if we substitute by its values, we can get the expression for V. So you can get V equal to, let's see what? We're gonna get, oh wait, I put 5 over 2 is 5 over 12, be careful. So we get 5 over 24 x squared minus 10. So this should be the shear equation. So now again, what type of equation is that? This is a quadratic equation. So how many points do we need? We need at least 3 points, no? Okay, so let's find 3 points. So there are 2 easy points, which should be what? V of 0 is equal to what? Negative 10. V of 12. So it would be what? 12, 144. I don't know. 144 times 5 divided by 24 minus 10. 20. And now, what do we need to know? Where is this point going to change directions, no? Okay, so in order to do that, how do we do that? We do dv dx equal to 0, which is going to give us what? 10x over 24, well, maybe 5 over 12. Should be 5 over 12, doesn't matter. Minus 10 equal to 0. What did I do here? Would be, here we take the derivative, so it should be 10. Oh, no, it's 24. No, here it's 12 times 2.
Yeah, 5 over 12, the derivative of 10 is 0.
Oh, yeah. Sorry for that. I'm not paying attention. Absolutely right. Sorry. So it should be 0. So basically, this is going to give you 0, no? So it's not going to give us anything. So this is only valid at x equals 0. Okay, not a big problem. We see what that means when we do the figure. All right, so now let's go and do for the other one. Let's see if we can find the moment. So this go from minus 10 to 20. Okay, we'll see how it looks like. Not a big deal. B, we need to find the bending moment. And for that, what do? We take the moments, but this time we don't have the choice about the moments. You always take the moments about which point? About the cut. Okay. So now let's be a little bit careful, because for the moments will be force times arm. So let's start the same thing we did here by the By. So we know By, so we take the moments about here. We know this one will be what? 10 times, what is the distance here? X, no? That moment will be going what? We'll be going counterclockwise, so that will be positive. All right. Now let's look at so the next one will be the moment M. Moment M is going clockwise, so that one should be negative. That way we took care of this one and this one, and now we can deal with the one of this load over here, of the triangular load. So this one will create a moment about the cut what? Going clockwise, no? So it should be negative. Now, what is the value of the force? So we did the value of the force. The value of the force should be 1/2 of 512x times x. So this is the force. And now what would be the arm? Arm should be that distance over here, no? Yeah? What is that distance over here? X over 3. Perfect. So this side is x over 3. This side over here will be 2x over 3, no? And this should be equal to 0. And basically, this is going to give us what? M. So if we did correct, what should we get? We should get the integral of this equation, no? Remember, that's what we're going to be doing next, but we're going to get M would be equal to 5 over 24. 24 times 3, 72. So we're going to get minus 5 x cubed over 72 plus 10x. Okay, I mean, there's nothing wrong. Maybe I should be a bit smarter and select positive going clockwise, but it doesn't matter. All right, so we get the expression for M over here. Okay, so again, I told you that I wasn't going to do the derivations. I'm going to add them to the notes, but I'm not going to do it in class. So page 15, with my last page of this notepad. Another one. So if you remember, we had let's start case B. Okay, what I was going to show you, I'm going to give you this page right here. Remember, we wrote this equation here. The distributed logs equal to dv dm and that the shear load is dm dx. Okay, we did that. I give you the equation. I'm going to add this derivation page to the notes, but really it's not that important. Now let's do case B. That way we save a few minutes. See if we have time at least to finish. So case 2. Let's see what is the notation I use for this one. Here, case 1. I did a square over here. Okay, so for here, let's say the steps 1 and 2 are identical, so that we have what? We have AX equal to 0, AY equal to 20, and BY equal to 10. Okay, we go to step 3, which is the shear and bending moment equation. Okay, so here, what happens that this time the figure for us is what? We have this, where this is AY, this is BY, but now we have this is equal to 5, this is equal to 0. We have this. So now what happens if we need to start from point A? So we start from point A, that means that this will be our X, and this will be our Y. Okay? So if we make the cut over here, how would it look like? So this time it's not going to be pretty, no? Because if we make the cut, basically what we're going to have is something like this. But now you're going to start from a certain point over here. Which is going to be like this. So you will know this one is 5. You will know here we should have V and M. But again, this should be X over here. And we have a Y here, which is 20. Okay, so maybe let's do the shear force, and we stop over here. Let's see if we have time to do that. So in order to do the shear force, what are you going to do? You need to apply summation of forces equal to 0. All right. So what are you going to have? You're going to have 20 minus V, but now comes the problem. What do you do with this force, with this distributed load over here? So if we don't want to use the equations that I showed before, that we'll do that next time, what would be the way to do this one? you can break this load into what? Into a triangle and a rectangle. So let's say this will be, the triangle will be 1 and the rectangular area will be 2. Okay. What would be the equation of this line? I mean, the slope will be the same as before, no? Which was what? 5/12 x. What would be the b? Y of 0 must be equal to what? So it should be, sorry, it should be negative 5/12, not positive because the slope is negative. So what will be the equation of this line? Plus 5, no? I will add on the notes the detailed derivation of that. I mean, what would be y of 0? Should be equal to 5. The slope is the same as before, but this time is negative. So if we do that correct, what should be the load? The value of the force of the triangular part should be minus negative 5/12 x plus 5. So it should be the height. Okay, let's do the first two. Okay, sorry for that. I think the way I wrote it, so this will be this part over here. The height will be minus 5 so it should be the height times x. So this should be, you put here 2. So basically the rectangular area, the rectangle. And I will stop for the next one. Now, what should be the value of the rectangular? So we know it's going to be 1/2, because we know it's a triangle of what? Should be, we start from this end. So we know it will be x times the height, no? So it's x is the run. How much would be the height? Would be 5 minus whatever is this height. So it's 5 minus whatever is this. Yes? Yeah? And that would be given by what? By the equation of this curve. So 5 minus 5/12 of x plus 5. Equal to 0. Okay, and we do the simplification of this and finish this problem next time. But you see, guys, it's getting, every time it's getting more complicated, no? And I guarantee you